Back in 1993, a conference on general relativity was held in Tübingen, Germany. At the very end of the conference, there was an exit poll where participants were asked a simple question about general relativity, to which 22 participants answered no, and only 3 participants answered yes. Then the question was slightly modified by adding one additional condition, and only 7 participants answered no, and 14 answered yes. What was this mysterious question, so that even after a century there is no consensus among physicists? To uncover what the question was, first I need to tell you what the problem is. And it goes back to the very famous twin paradox. In standard formulation of the twin paradox, the situation is the following. You have 2 twins, one remains on Earth and one takes a long trip to a distant star, turns around and go back to Earth. When they compare their clock, they will find out the traveling twin is younger at the reunion. The reason behind this is that special relativity teaches us that moving clock ticks always slower than stationary one. However, special relativity also teaches us that every inertial observer in a universe has the equal right to claim being stationary. Therefore, if you try to describe the situation from the other twin point of view, for him the observer on Earth is moving and his clock should tick slower, and therefore he should be the younger one. This paradox is then easily dismissed by saying that only the observer on Earth was inertial the whole trip. So any explanation on the internet you will ever find on this paradox will always treat these 2 observers asymmetrically. Because you can sketch the space-time diagram for the whole trip only for the observer on Earth. But you can't sketch it like this for the traveling observer. So again, anytime you sketch a space-time diagram for some object, you define at least one inertial frame, and therefore any acceleration is treated as absolute relative to this frame. And therefore, paradox is not a paradox. Before the discovery of general relativity, Einstein focused mainly on the experiences of the observers. He imagined that observer in a free fall would feel the same physics as an observer floating in space. By this, he came to the conclusion that these 2 observers are fundamentally of the same nature. And this led him to the discovery of general theory of relativity. But let's bring this idea to the twin paradox. Let's focus only on experiences. Imagine you are placed in some box with a small window. At one moment in time, you meet your twin in another box having the same age, and then you separate. And after some time, you meet again. The question is there a way how to determine who should be younger one at a reunion just based on the experiences you had? In principle, what you can measure inside the cabin is time and acceleration. And in this article by Ericsson and Gron, they found out that it's always the twin with the highest overall acceleration that is the younger one at a reunion. So it seems like we can determine the age difference purely based on the experiences of the observers inside the cabins. But one might ask, is this generally the case, also in the curved space-time? To answer this, consider a different scenario. Consider a rocket hovering above the planet, so the engines produce just enough thrust so that you keep your position fixed relative to the planet. Your twin is shoot upwards, and at the moment he's at the same location as you synchronize your clocks. Now your twin continues freely falling without thrust, and eventually you will meet him again at the same location. After the trip, you would find out that you, as a stationary observer, are the younger one at the reunion. So again, the observer who is feeling the most force is the younger one at the reunion. In physics, we distinguish 2 types of acceleration. 3 acceleration, which is just a coordinate acceleration and is non-zero every time you measure the change of velocity with respect to time. Let's call it A3. But we also have 4 acceleration, which is much more abstract, but simply it is always non-zero every time you feel g-forces. In flat space-time, non-zero 3 acceleration also means non-zero 4 acceleration. But in general relativity, non-zero 3 acceleration doesn't imply non-zero 4 acceleration. For example here, the observer in the rocket has 0, 3 acceleration and non-zero 4 acceleration, whereas freely falling observer has non-zero 3 acceleration but 0, 4 acceleration. So if you are freely falling observer, or in other words, you are moving on a geodesics, you have 0, 4 acceleration. It was thought that if you are moving on a geodesics of a space-time, you are moving on a curve with maximal proper time, and therefore you are aging the fastest compared to all other observers. And in order to deviate from the geodesics, you need non-zero 4 acceleration. Or in other words, rocket engine on. So it seems like we could generally say that observers with the highest 4 acceleration are always the youngest one at the reunion. However, in this article by Marek Abramovich and Stanislav Bajtlik, they considered different scenario. You are still hovering about the planet, but your twin is now orbiting the planet. The moment you meet, you synchronize the clock and wait for the reunion. Your twin had 0, 4 acceleration the whole trip, but non-zero 3 acceleration, while you had 0, 3 acceleration and non-zero 4 acceleration. At the reunion, surprisingly, you find out your twin is younger than you. So geodesics is not a path of maximal proper time. It's a path of the extremal proper time, but the time can be either maximal or minimal. This implies that there is not a single parameter that would ultimately determine who should be the youngest twin, but it also implies something else. It implies some absoluteness of angular velocity. But anyway, if you ever decided to put the twin paradox to a real test and leave the planet to a distant star system and back, it might not be this you come back to, but this. But seriously, hear me out. In today's world, it is impossible to live without negative impact on our planet. Whether you are using electricity, driving a car, or simply buying food in supermarket. This creates deforestation, plastic pollution, and brings some animal species on the brink of extinction. And every one of us is involved. But it doesn't mean you have to go out and clean up the mess yourself. But you can support communities that will do it for you. Planet Wild is a nature protection organization that is funded by the community of around 13,000 people. And their goal is to bring back the endangered species, protect our oceans, or restore forests. Think of it like a crowdfunding for nature. They document all their projects through video reports that you can find on their YouTube channel and app, so you can directly see where your money goes. It's also very fun and informative to watch their project video they upload every month. Like in one of their recent projects, where they cleaned one of Europe's most polluted rivers to stop plastic from getting into the ocean. So if you care about the nature, consider becoming a member. You can choose whatever amounts fits for you. You can start for as little as the price of a sandwich. Every dollar counts. And because I think they are worth supporting, the first 100 people who sign up using my link Physics10 will get first month paid by me. So scan the QR code or click on the link in the description. You can cancel anytime without questions. Now back to the video. In the years between 1910 and 1920, when Einstein was building his theory of general relativity, he wanted his theory to satisfy the so-called general principle of relativity. But let me pause here, because this creates a lot of confusion around general relativity. Because today we think of general principle of relativity differently than Einstein did. For Einstein, general principle of relativity meant that all motion is relative in the same sense that inertial motion is relative in special relativity, including accelerated motion. He thought that all motion, including acceleration, can be always measured only relative to distant masses like stars, but you cannot do it locally in empty universe. So in his mind, there should not be distinction whether it's you who is accelerating or all the masses in the universe except for you. Similarly, there should not be distinction whether it's you who is rotating or the rest of the universe is rotating. This was inspired by the work of Ernst Mach, and Einstein wanted the theory of general relativity to be fully Machian. It's my opinion that Mach's principle can be taken as a foundation for the theory of gravitation. Einstein believed this will be achieved if he creates a theory that satisfied the so-called general principle of covariance. This principle of covariance means that you can always write the equations of motion in their simplest form in any frame of reference, including the accelerated ones. And eventually, he succeeded. He found equations that have the same form for observers in any kind of motion. He believed that he created a theory that fully obeyed the Mach's principle. Inertia has its origin in interaction between bodies, as was first recognized by Mach. But now, let's look back to our twin paradox scenario. Einstein thought that the true solution to the paradox is the following. The traveling twin would say the clock on Earth is slower because it's moving. But when he turns the rocket engine, due to equivalence principle, he can still claim to be stationary, but the rest of the universe is accelerating towards him, which creates a uniform gravitational field in the universe. The Earth's clock is higher up in this gravitational field compared to his own, and therefore tick much faster. After the acceleration, the Earth twin will have much larger time on his clock, and the rest of the journey will tick slow again, but eventually will show larger time. But this was all kinda made up. Einstein didn't provide any calculations that would show that the accelerated universe would create such gravitational field. But he didn't even need to see that this picture cannot be fully correct. Equivalence principle works independently from the existence of distant masses. And in any of our solution to the twin paradox, we didn't need any relation to distant masses. General relativity has enough tools to solve it locally in empty universe. But if the universe is empty and you have only one twin waiting for you, there is certainly not enough mass in the universe to produce gravitational field during your acceleration. So this accelerated twin would experience gravitational field that is without any cause. And since the gravitational field is without any cause, then you can safely say that he is accelerated and not stationary, and therefore Mach's principle is broken. Similarly with orbital motion, if you consider you are at rest and the universe is rotating around you, then the distant stars would have to rotate faster than light. And therefore, it is safe to say that it's you who is rotating and not the universe. But overall, one can clearly say how much someone is moving by just measuring how much he is aging. And therefore, there is some fundamental absoluteness in motion. If the Mach's principle was valid, then the twin paradox would be unsolvable. Later, Einstein himself let the Mach's principle rest in peace. One should not speak any longer of Mach's principle, but rather of Mach heuristic. He downgrades the Mach's principle from a law to just a guiding idea. It's true that Mach's principle played an important role in my work on general theory of relativity, though I must admit that this guiding principle has not led to a completely satisfactory theory. He admits that GR does not fully realize Mach's principle. And this brings us to the first question asked at the conference. Is general relativity perfectly Machian? To which 22 participants answered no, and only 3 participants answered yes. But I just provided arguments why general theory of relativity cannot be fully Machian. And even Einstein realized this. But still, 3 participants answered yes. I'm not sure why, but I have a theory, and it's connected to the second question that was asked. The reason why Mach's principle is broken in general relativity and we can solve the twin paradox without the relation to the distant masses is because we assume that space-time infinitely far away from any massive object is flat. We call it asymptotic flatness, but if you have any region in space-time that is flat, then you can relate any accelerated motion relative to this flat boundary. But what if the boundary wasn't flat? Could we save the Mach's principle? General relativity supports the existence of one effect that is very Machian. It's called lens-tearing effect, and it means that accelerated motion can do a frame dragging. If you have a rotating mass, then an observer hovering at a certain distance would slowly gain angular velocity due to frame dragging of the rotating mass. If you did the calculations, you would find out that the observer freely dragged would age faster than observer trying to counteract the dragging. Now imagine you are in empty universe, and there is a shell of mass around you. The mass of the shell is given by the so-called Schwarzschild radius. The Schwarzschild radius basically means that the radius of a black hole with that particular mass. For example, a Schwarzschild radius of Earth is just 9 millimeters. So the higher the Schwarzschild radius of the shell, the more massive it is. And if it has the Schwarzschild radius above its own spatial radius, then it becomes a black hole, since the shell is below the horizon. Now imagine you are inside a shell with a Schwarzschild radius much smaller than the radius of the shell, so you are not in a black hole. Now this shell starts to rotate with angular frequency omega. According to lens-tearing effect, this should cause you to co-rotate with the shell. This effect meant to be the proof that Mach's principle is valid in general relativity, that rotation is in fact relative, and we can only talk about rotation relative to the shell, and not about the rotation in absolute sense. Because now, the observers that are freely dragged would age the fastest, and could therefore consider themselves as stationary. But, in order to save the Mach's principle, you would need an exact match between angular velocity of the shell and the observer. This means perfect inertial dragging. But if you calculate the amount of dragging, you get this formula. It depends on the Schwarzschild radius of the shell, and therefore its mass. If the shell is very light, the dragging is only partial, meaning the observer will not match the angular velocity of the shell, and therefore we can still talk about absolute rotation relative to asymptotic flatness of the universe. This expression, though, was only derived for a big field approximation, and therefore it's not valid for a large Schwarzschild radius. But later in 1966, Brill and Cohen found an expression for strong fields, which looks like this. Now, if you put the Schwarzschild radius to be the same as the spatial radius of the shell, then you get a perfect inertial dragging. Now, the shape of the universe at the boundaries is irrelevant. Now, the rotational motion can be only taken relative to the shell. The question is, can we have perfect inertial dragging in our universe? The universe has the so-called particle horizon. It's the furthest region of space from which any information could reach us during the age of the universe. This is the part of the universe with a causal connection to us, and its radius is around 46 billion light years. Knowing the density of the universe, you can calculate its Schwarzschild radius. You would get a number around 14 billion light years. This is surprisingly close to the size of the observable universe. It is basically the same order of magnitude, but there is also a huge error if you try to estimate the density of the universe. So in principle, the condition for perfect inertial dragging could be satisfied in our universe. But what about linear dragging effect? Could a shell of mass accelerated cause full dragging to explain relative acceleration? Well, I don't really know, unfortunately. There is an article from Gron and Ericsson about translational inertial dragging, but they used a linearized metric to find the solution. This means that the solution only works for weak gravitational field. And it's better, because this would mean that a shell with a radius equal to the Schwarzschild radius, accelerated at 1g, would produce even stronger dragging acceleration for the object. This would be nonsense, right? And clearly not Machian. But I couldn't find a strong field solution. But I can imagine it's very difficult to find. But I can very well imagine that full drag when the radius of the shell is equal to the Schwarzschild radius is possible, if it's calculated properly. If so, then this would mean that with a proper boundary conditions, our universe could be potentially perfectly Machian. The interesting thing is that if you have evenly distributed mass density in an infinite universe, then with increasing the shell radius, the Schwarzschild radius rises even faster, eventually always catch up with the radius of the shell. As the time grows, the particle horizon of the observable universe is slowly growing. And if the universe is infinite, eventually it will reach the point where its radius will be equal to the Schwarzschild radius. So eventually even our universe could reach the size where the Mach's principle is fully valid. But the general relativity doesn't need this. It works perfectly well in empty universe. So this is more like a philosophical satisfaction. Also, the rotating black holes have upper bound for how big their angular velocity can be. So if you have something that locally spins very fast, you can't say it's at rest and the shell is rotating. This connects us to the second question the participants were asked at the conference. Is general relativity with appropriate boundary condition of closure of some kind very Machian? To which only 7 physicists answered no and 14 answered yes. Now I have a theory why in the first question 3 participants answered yes. And it's because they didn't expect the second question. But remember, the second question was about whether there are such boundaries mathematically, but not applied in our universe. So today, when we say general principle of relativity, what we truly mean is the general principle of covariance, but not relativeness of all motion. So be mindful of this when you read some literature. Mach's principle has influenced me very greatly, though I was not able to formulate it precisely. It still plays a role in my meditations on gravitation, though I am not sure to what extent it will withstand the test. That being said, don't forget to check out the Planet Wild community. If you wanna see them in action, watch their video about fighting ocean plastic pollution. I enjoyed it very much, and if you wanna become a member, click on the link in the description. Thank you for watching. Bye.